Today we are going to learn the asymptotic notations, one of the most important topics in design and analysis of the algorithms. So don't worry if it sounds difficult, I'll explain everything step by step with easy examples. Why we need the asymptotic notations? Imagine you are traveling from home to college. The time depends on traffic, vehicle, and the road conditions. But we want to know how the time increases when the distance increases. That is exactly what asymptotic notations do for algorithms. We focus on growth, not the exact time. So, asymptotic notations describe the growth rate of an algorithm's time or space complexity as the input size increases. Or asymptotic notations are the tools that are used in the analysis of algorithms to find the growth rate of a function. So next is the types of notations, big O, omega, and the theta. Asymptotic notations help to compare the algorithms independent of the hardware. Big O. Big O represents the upper bound of an algorithm's growth rate. It describes the worst case performance. So big O is like asking what is the maximum time it can take to reach the college. When traffic is very heavy, signals are slow and roads are crowded. Even if sometimes the road is free, we always prepare for the worst traffic. So big O is the worst case scenario. Big O is planning for the worst situation. Here is the example: f of n is less than and equal to cg of n, and f of n is equal to 2n square plus n, and g of n is equal to gn square, and the value of n is equal to 10 and c is equal to 3. By putting the values in this equation, f of n less than and equal to cg of n, by calculating this equation, we find that 210 is less than and equal to 300. So the time complexity of the big O is the n square. And here is the graph of the big O. F of n is less than Cg of n. The blue line shows the C of n, and the red line shows the F of n. Next type is the omega. Omega represents the lower bound of an algorithm's growth rate. It describes the best case performance. So omega is the best case performance. Imagine you leave early morning, no traffic, green signals, empty roads. So this is the minimum time required to reach the college. Omega is the best case scenario. So omega shows the fastest possible performance. So f of n is greater than and equal to cg of n. By putting all the values, we find that 210 is greater than and equal to 200. So the time complexity of the omega is the omega n. And here is the graph of the omega that shows f of n is greater than and equal to the c of n. Next type is the theta. The theta represents the average case of an algorithm's growth rate, or when upper and the lower bounds are the same. It describes the average and the tight bound performance. Theta is like traveling during the normal hours. Some traffic, some signals, normal conditions. Most of the time, this is what actually happens. So, theta is the average case performance. Theta tells us what actually happens. Here is the example. By putting all the values in the equation, C1g of n is greater than and equal to f of n is greater than and equal to C2g of n. By putting all the values, we find that 300 is greater than and equal to 210, and 210 is greater than and equal to 200. So we find the time complexity of the theta is that theta into n square. Here is the graph of the theta that represent C1 of n is greater than f of n and f of n is greater than C2 of n. Next, little o, also known as the small o. Little o represents the strict upper bound of an algorithm's growth rate. Little o means one runner is always slower than another runner, no matter how long the race is. For example, walking the speed compared to bike speed. Little o grows the strictly slower. Next is the little omega, also known as the small omega. Little omega represents the strict lower bound of an algorithm's growth rate. Little omega means one method is always faster than another as the input size increases. For example, bike will always beat the walking for the long distances, so little omega grows strictly faster. In the big O notations, we ignore the constant and the smaller terms. So why we ignore the constants in the asymptotic notations? For example, if one pizza takes 10 minutes and two pizzas take 20 minutes, but when you order 100 pizzas, the exact minutes don't matter. Only how fast time increases the matters. That's why we ignore the constants in asymptotic notations. So remember, big O is the worst case performance, omega is the best case performance. Imagine the empty road, and the theta is the normal day, that is the average bound. Little o always slower and the little omega always faster. If these real life examples helped you understand the asymptotic notations, like the video, subscribe the channel and comment more examples.